General Physics 1. And now, here's your professor, Varanga Pereira.
Hello everyone, welcome to the class. This is Physics 317K, or General Physics 1. We're excited to have you in the class. To get started, let's go to the slides here. I want you to start thinking about what is physics. You signed up for this course, so let's talk about what did you sign up for. The reason why I'm showing you this video here is to already start thinking about where you might encounter physics in everyday life, and something like walking, which you do pretty frequently. So you have to walk about, move about, even if you are talking about moving through using a vehicle, so something like a bicycle or a car. How you go about this seems obvious maybe because you've done it for a while, but let's think about what's actually happening. What makes this all work out? Why are you able to walk across the floor? What forces are involved? Do you need forces? This is getting you to think about, hey, where would you see this stuff in real life? Throughout this course, 317K in particular, basically everything we're talking about, it has some relevance to everyday life. You should always be thinking about, hey, where have I seen this? Where can I see this? And also, as you learn new concepts in this class, you can go and try to see as you go on a vehicle, cook food, what have you, you're thinking about physics concepts as you go. What is physics? One way to say this is it's a field of study that tries to describe the fundamental mechanisms that underlying every phenomenon in nature. Another way to think about this is if you're a 5-year-old, or you have a relative who's a 5-year-old who asks a lot of but why questions. If you really ask anything related to nature that is, why does that happen that way? Eventually, you have to deal with physics. Eventually, it will be something in physics that is the underlying mechanism. Why is the sky blue? Why can you walk? And things like that. In this class, we're going to talk about a number of topics. We'll start off with motion, and we'll get into forces. So think about where are you seeing this in everyday life. So on the left, some water dripping, some motion of the water. In case of forces, here's this ant transporting a leaf or something next to a banana. Where are these forces being applied in nature? That's the next thing we're going to talk about. We'll also talk about fluids. So a lot of you are in the life sciences, so a lot of the examples we're going to use are in the life sciences. So you might think about collecting blood or an IV or something like that where fluids are involved. And then thermodynamics, think about cooking food. You're making pasta or something like that. That's where you might see the topic of thermodynamics. So lots of different topics. If you look at the syllabus, a number of topics are listed. But believe it or not, the entire class really relies on two big ideas in this whole class. So the 5 weeks we're going to spend is basically these two ideas over and over again. At the end of this class, you should really understand these two. These are really important. But at the beginning, you don't have to worry about all the symbols and what these means and what's P and what's F, and we'll get to all of this in a second. But these are the big ideas that you want to really understand. Force and momentum, they're connected. There's a principle associated with force and momentum, and there's a principle associated with work and energy. One thing to start off with is the words that we use in this class have very specific meanings in physics. Think about work. It's not like a 9-to-5 job kind of work. Work in physics is a very specific thing. And so when you use terms like speed and velocity, be careful because in everyday life we kind of use them slightly differently, maybe less precisely. So in physics we have these very precise meanings to words. So let's just be aware of that before we get going. Okay, so two big ideas. And this is getting at the heart of what physics is, that physics has few very fundamental concepts and everything else is derived from those fundamental ideas. Like I mentioned, a lot of you are in the life sciences. You have majors in neuroscience, biochemistry, biology, things like that. You might be very familiar with life science courses and textbooks where you are very familiar with biology, say. And I want to contrast this with physics, not to say any one of this is better than the other. It's not. It's just to show that they're different. So the certain things you do in biology, you don't want to do in physics, and things you do in physics, you don't want to do in biology. In biology, you're dealing with very complicated systems. So if you're talking about the human body, We can all agree it's a very complicated system. Nobody's looking at the human body thinking it's a very simple thing. But in physics, we're dealing with very simple models. We'll draw spheres and we'll draw boxes, and the models themselves are not that intricate. They're very simple models. And in biology, you're dealing with things that are qualitative. You're describing. So if you're doing a dissection or something, you're describing what you're seeing. In physics, it's more quantitative. You're dealing with more math, more numbers, more quantitative aspects. In biology, also dealing with specific examples. So if you look at eye of a human, the eye of a dog, and eye of a dolphin, or you look at different eyes, yes, there's probably some things that are common, but you're not going to have somebody, an eye doctor for a human, kind of just showing up the next day and doing an operation on a dolphin. It's not going to happen that way. They're specific to certain examples. And like from the slide before, in physics, it's a different way. These broad principles that cover everything, humans to the universe to galaxies, everything. We're trying to find what those principles are, and they're very broad, and they're not supposed to be specific to a certain example. Let's do this with an example of the circulatory system. If you go to a biology textbook, you can look up the circulatory system, and it's very complicated. This is what you would encounter in, let's say, a life science class. In physics, you can look at the circulatory system and think of the rough sketch, that there may be a main vein that branches off, and you try to think about general principles. So if you look at the right-hand image, yes, it could apply to the circulatory system, but you can think about this in a way that's kind of like the plumbing in your house. What are those general ideas that work for the water running through your house as well as blood running through the body? So in physics, we want to think about general concepts of how fluid might flow versus a specific situation with the human body. Okay, so a little bit of physics, just give you a little advertisement of what's coming up ahead, what the subject is all about. Where we're going to start off with is this topic called kinematics. It's a fancy word for describing how things move. So here's a bird. Think about a bird flying. Think about you walking. Think about tossing a ball. We're not concerned about why something's moving. That's going to come later. So kinematics is describing how things move. So without physics, you can say it's going to the left, it's going up, it's going fast, it's going slow. They're kind of qualitative descriptions of what you're seeing. So imagine you're at a park, you're seeing a bird, and you're with a friend, you're describing what the bird is doing. You can describe it's this kind of bird, it's flying up or down, or is hunting prey or whatnot, but it's very qualitative. So in physics, what we want to do is make it precise, give it a number, and that way, not just you, your friend, somebody else in some other part of the world, everybody can agree how this bird is moving is in such a way. So you want to be a bit precise. To get you to think about birds as an example, why should you care about how things move? Here's an example of birds migrating. So southern hemisphere to the northern hemisphere, and they'll go back. Each dot so there are about 118 species of these populations of birds that are kind of migrating up and down. And all the dots are a collection of birds. And so when this is happening, you really can't say that way. You can't say up. You have to be a little bit more precise on how are these birds moving. And that's why we need terms like speed and velocity and acceleration and position and displacement. All these terms are used to precisely describe what something in nature is doing, like in the case of the birds migrating from the different hemispheres. In this class, the terms we want to understand: position, displacement. So like I said before, if you were to use this in everyday life, you might use the word position and displacement kind of interchangeably even. Maybe you don't use the word in displacement, but when you say the position, what do you mean by that? It's imprecise in everyday life, but in physics we'll give you a very precise meaning. Position and displacement, not the same thing, and we'll distinguish the two. Then we'll talk about average velocity. We'll talk about how that compares to instantaneous velocity. We'll also talk about speed along the way, because speed is probably something you hear about more in everyday life. So Let's go to the doc-chem. Like I said, this is where I'm going to be most of the class generally. So starting with the next class, most of the class period is going to be me writing on the notes here. That way you can follow along, take your own notes. So let's talk about motion in one dimension. Okay. So what is a dimension? A certain direction that something can move. So generally in your room, wherever you are, you can think of something like some object. Here's a paperclip. It can move up and down. That's an independent motion. So if I say this clip is moving up and down, it isn't moving left and right. If it's moving left and right, it's not moving up and down. So that's independent. So those are two different directions. And then the third is, of course, up and down. So it can go up and down this way. So those three dimensions, usually depicted in X, Y, Z, are what you normally would encounter in everyday life. You have three-dimensional motion. When a car is moving, it's moving through to three dimensions, usually. There might be cases where it's mostly two-dimensional. So if you're playing pool on a pool table, you're shooting, the balls are moving across the table, mostly in two dimensions. It's not really unless you shoot a bad shot and the ball flies off the table. Mostly the balls are on the table. So that's a two-dimensional case. Now, we start off with one-dimensional motion just so that it's easier to describe. Once we know how to deal with one-dimensional motion, we'll talk about two, and then that way you can extend it to three. So this is very physics in the sense of let's not deal with the most complicated thing first. Let's build small steps along the way to talk about the thing that's actually complicated, which is three-dimensional motion. Birds, for instance, three-dimensional motion. Okay, so motion in one dimension. The first thing we want to talk about is position. As something moves, what is its position? Let's take an example. Our example could be an object like a book. And when you say, what is the position of the book, you have to think about relative to what? So the book's position is a relative thing. If you want to give it a position, you have to base that position off of some reference point. In this case, it could be the floor. And our position we can depict with X. And we can say so let's say meters or something like that, the book is so many meters or feet off the floor. So that is its position. It's not its only position. So a book can have a position relative to the center of the earth. That's a different number. The book can have a position relative to Jupiter. That is different from this. So position always depends on what are you basing this on. What is the relative point you're measuring from? In this case, the table. You can measure from the roof. You can do that. And position, as we start, we'll change this later. To start with, we're going to say this is a scalar quantity. And we're going to contrast this with vector quantities. So there are certain things that are scalar, certain things that are vector quantities. And position is grouped into, for now, a scalar quantity, where it has a certain magnitude, it has a certain number to it, and it has certain units to it. So in the case of position, you might say it's 11 meters off the floor. So that it has a certain number and it has units associated with it. And that's what makes it a scalar quantity. We'll come back and talk about a slightly different quantity in a second. So this is position. Let's now talk about displacement. This has to do with not just where something is at a particular time, but how it's changed. So here's our book to start off with. Maybe you're holding it up off the floor, and if you let go, the book is going to fall. And it might be here at a later point in time. Here's your book. And once it falls down, it's somewhere here. And displacement is that difference between what was its position before. You can use x naught or xi for initial, just a subscript to keep the two different positions separate. And we can say x final. And notice when we say f for final, it's not at the end of time. It can just the end of the time period you're considering. So we're considering this to be the start, this to be the stopping point. even if it is going to continue on down to the floor, we're freezing this between this and this. So this becomes our initial, or x naught, and then this becomes our xf, which is for final. And displacement, we're going to use the Greek symbol delta x. Displacement is delta x is equal to xf minus x naught. It's the difference of these positions that makes up a displacement. And the units are still the same. So it can be meters or feet. When I use these square brackets, units, if I say m, I might mean mass, the variable. So when I'm talking about units, I put these square brackets just to say I'm talking about units and not variables. So the units of position and displacement are the same. We have where something is. If you want to locate a bird, you want to locate a book, where is this thing? That has a certain position. After it moves, it has a certain displacement. What was it before? What was it after? That difference becomes a displacement. Okay, so now you have described where something is and where is it at a later point in time. And that's a good segue to talk about velocity. We'll talk about average velocity. Okay. And velocity is generally not a scalar quantity. We're going to use it as a scalar quantity to start with, and then we'll give it its proper place, which is a vector later. But for now, for simplicity, let's start off talking about it as a scalar quantity. And what we're going to do is write average, V, the bar means average, is equal to the displacement divided by time. Okay, so we're building off of our terms. We're taking position and basically using the idea of position, we came up with displacement. And using the idea of displacement, now we're going to build this idea of an average velocity. What is the displacement over the time period? So if you're talking about this book falling, it fell by 2 meters, 3 meters in a certain amount of time. So that's what we're after in terms of the average velocity. We'll take the delta x, our displacement, divided by delta t, our time period. So delta x, we said before, is xf minus x naught divided by tf minus t naught. Two different times, initial time, final time. It's always final minus initial when you're doing this difference. So you have a displacement over time. So think about units always. So we wrote up a new equation, but think about the units. So we have a displacement, units of which are meters, and then the time we can write in seconds. So for lengths, SI units, standard units are meters, you might know. For time, SI units are seconds, standard units. So if I switch back to the computer real quick, I'll show you a handy chart. If you search for NIST, SI units, National Institute of Standards and Technology, if you type in NIST, SI units, if you click on this link, there is this chart you can download, print it out if you want, keep it near you. Pretty handy in terms of the SI base units. You'll notice that there are only 7 fundamental units. For time, it's seconds. For length, it's meters. For mass, we'll talk about that later, it's kilograms. So for our class, we're going to need these 3 mostly. A little bit towards the end, we'll talk about Kelvin in terms of our temperatures. Then in the next class, Physics 2, we'll get into amperes, which is the current. Moles you've seen from likely chemistry. Candela is rarely used. It has to do with luminosity, brightness of light bulbs and things like that. You're rarely going to see that, but if you want to, that's one of the base units. And everything else, if you talk about a Newton or a Coulomb or Joule or watts or Pascal, everything else is derived from these 7. So keep those in mind. Pretty nice chart. If you want to download it, keep it handy. If you want to remember what are the base units. So for length, remember meters, time is seconds, kilograms we'll get to later. Okay, going back to our notes here. We want to also think about this graphically, right? That's where the calculus comes in to help you once we think about what this is graphically. Okay, so let's try to plot this, okay? Yes, it's an equation, but let's think about what this means in terms of a plot. So let's plot our position as a function of time. And I'm going to make up a curve here. It doesn't matter what it particularly is. I just want to have a certain example. So let's say the position over time looks like this. So we have an object that has some value, let's say 10 meters or something, and it goes to 0 at some point in time. Maybe it's falling. So if we think about two different points along the way, this could be our initial, this could be our final, but we don't have to restrict ourselves. These are arbitrary points. What is initial and what is final? It can be anywhere along the way. So why don't we pick 2 points? Let's say this point and this point to be our initial and final positions. So let's do this, where this is our initial position and this is our final position. This plot is showing you something that's maybe falling down to the ground because it has a certain position, kind of like our book. It has a certain value of position, and then eventually it hits the ground, goes to 0 at some point in time. So what we want to do is pick 2 points along the way, where the book maybe is here and the book is here, and then identify at what point in time are we talking about. So this is time initial, this is time final. So now let's go back to our average velocity. So when we said average velocity, we said that's equal to the xf minus x naught divided by tf minus t naught. That's our definition of what the average velocity is. So average velocity is the displacement over time, xf minus x naught, divided by tf minus t naught. So if we write that, think about what that's saying here in terms of the plot. Is there something in math that kind of looks like this? A math concept that kind of looks like this? Averages, yeah. Something graphical, yeah. Slope, yeah. Remember what a slope was. You remember from your math class, there was a rise over a certain run. This is that rise part. There's a change in kind of the vertical component of your plot over the horizontal component of your plot. So when you plot, when you actually calculate this number, xf minus x naught divided by tf minus t naught, what you're getting is the slope of these 2 points. So let me try to draw a straight line approximately. So when you are doing this, what you're finding is this number is the slope of that line. You have a certain slope between these 2 points. That becomes your average velocity. So when you think about this idea of an average velocity, think about how do I take a position versus time plot and think about it graphically. It has something to do with the slope of that line. So that's what the velocity represents. Now, what you can do is think about what happens if you take that same curve, same scenario, the book may be falling to the ground. If you have that same curve, what happens if you picked not just these 2 points, but you picked 2 points. So let's keep the initial the same roughly. Let's say the initial is still there, but you considered the average velocity at these 2 points, closer in time. Because if you draw the position is like that, and then time is like that, it's a smaller time period because you've squeezed this a little bit. So instead of these 2 points, you're trying to find the average velocity between these 2 points. So now think about what would happen to the slope. So the slope won't be the same. because the slope for these 2 points will be something like that. So that average velocity really depends on the time period you're talking about. So as this book falls to the ground, when you say what is its average velocity, it depends on how long you're counting for, because its average velocity changes at different points in time. So you can't just have a number and be done with it. You're to be more specific. What do you mean by the average velocity between what 2 points in time? Because if you do this, it gives you a certain number. You do this, you get a different number. Now, you can take this to its limit. You can take it to a certain extent where, well, let's say we'll take that same scenario again. So x and t, and then same curve. Trying to roughly draw that same curve again. Keep the initial position that we're considering the same position. But instead of having this duration in time, what if we put these 2 points right next to each other like this? We can do that. So in that case, the slope, that would be the slope. So here's the slope, here's the slope. And that's when you start seeing this idea of an instantaneous, if I can spell, instantaneous velocity. Think about what's happening. So that's graphically what's happening to the average velocity. If you're taking the average velocity over a smaller and smaller time period, it approaches a value that's instantaneous. Maybe another example is thinking about a car. You're traveling by car. You might start at a certain speed, change, go to a rest stop, speed up, go back to the highway. Your velocity, your speed is changing throughout the journey. But you might say, what was my average? You might do the whole trip. You may be on the road for 3 hours, and you might say, okay, where did I start, where did I end? And then over 3 hours, you have a certain average velocity. But you might say, that's not the number that's read on the speedometer. If you're driving, the number that shows up on the speedometer is this instantaneous velocity. At that particular instance, how fast are you going? And the way you find that graphically, if you could plot your journey like this, position over time, is to do this. Is that you're trying to find the slope between these 2 points that are really close together instead of far apart. Because the further apart they are, it washes out some of the detail and kind of averages things out. And if you want, that's great, but sometimes you want the instantaneous one. You don't care about the average, you want at that particular moment in time. In hour 2 and 15 minutes into the journey, how fast was I going? Instantaneously. So that's graphically, mathematically how you get there is you say we start off with the average. Okay, that's our average velocity, our definition. And what I'm going to do is I'm going to change some of these symbols just to make it a little bit easier to follow. So x naught, I'm just going to swap it and call it x of t, position as a function of time. Just changing the term, it's the same thing. It's just going to make the math look a little bit easier to see. The final position, I'm going to say, is the position at time t plus some delta t. So take a moment to think about what that means. So the initial position is some position as a function of time. So the initial position is that. The final position is that position plus a little bit more time. You're taking this function of position, taking that time plus a little bit more time. That tells you what the position is at the final point. Think of position as a function, time as a function of time, and depending on the time period you put in, it'll tell you what the position is at different points. We're going to swap this. What I'm going to do is rewrite the average velocity kind of like this, x t plus delta t minus x of t divided by delta t. All I'm doing is rewriting the average velocity equation. This is perfectly fine. This is very good for certain cases, but we're going into calculus, as you can probably tell. This is much easier to work with when you formulate it in this way. Still, this part is the final position, this part's the initial position, this part is just still the duration of time. So the mathematical way of doing this equivalent, of squeezing the 2 points together, is to say, I'm going to take the limit when delta t, that duration of time, is 0. So I'm going to take it and make that duration time approach 0. What happens to this function? This average velocity, if you take it to the limit where you squeeze delta t smaller and smaller and smaller, what looks like this in calculus? Seen something like this before? Somewhat familiar?
The derivative of the slope.
Yeah, derivative. Were you going to say something too, up in the front?
Oh, I was just going to say derivative.
Derivative, yeah. So if you look at your calculus textbook or your notes from calculus, this is defined to be the derivative. So this is the derivative of position as a function of time over time, dt. This is the derivative. You can write it this way. You can write it as x prime of t. You can write it as x dot of t. These are all the same. Depending on your calculus professor or instructor, they might have used different symbols. Doesn't matter. This and this, all the same thing. So this is perfectly fine. This means take a derivative of the function of x here. So the instantaneous velocity is defined to be the derivative of x with respect to time. So this is our instantaneous velocity. Now, this is not an algebra concept. This is certainly in calculus. The average velocity is algebra. You can get away with algebra. If all you care about is an average velocity, you don't need any calculus. But the idea of an instantaneous velocity, you need calculus to even get there. It means that how is this function changing as relative to time? When you take a derivative, that is what your instantaneous velocity is, and that's a concept that's in calculus. You can't do it without calculus.